So we have discussed in the last class, I told you energy difference of 4s and the 3D orbital. As I told you, whenever the examiner asks electronic configuration of any of the transition element or a D block element, so we are supposed to write down 4s subshell first, like 4s orbital first, then the 3D. Okay, remember. So I told you till here. So now we are supposed to discuss physical properties of transition elements. Okay. Now we are supposed to discuss the physical properties of transition elements. As we discussed in IGCSE or O levels as well, so it's the same, but we have to discuss in a more detail, right? So I can say that their boiling points are high, their melting points are high, or they have a variable oxidation state. Okay, they have a variable oxidation state, or I can say they can be used as a catalyst. Okay, or I can say they are going to form a colored compound. Okay, they are going to form a colored compound, or they are to have, why they are going to have high density, and why they are going to have high melting point and boiling point, or I can say they are having similar, they are having what? They are having similar ionization energy. Like, what do you mean by this? If you can notice electronic configuration of all the D block elements, okay? If you can notice all the electronic configuration of the D block elements, so you will see that it's gonna be like, let's say starting from scandium, proton number is 21, 3D1, then 3D2, then 3D3, then 3D4, then 3D5, then 3D6, then 3D7, then 3D8, then 3D9, then 3D10. So it's the same trend that they are going to follow. Only the number of electrons are going to increase in the d orbital. Okay, only the number of electrons are increasing in the d orbital. Okay, so on the basis of an electronic configuration, we can discuss we can discuss everything. We can discuss everything. Okay, so first of all, I'm going to discuss the physical properties of transition elements. So physical physical properties of transition elements, right? Generally, their melting and boiling points are higher. Generally, their melting and boiling points are higher than the group 1 or group 2 elements, than the group 1 and group 2 elements. Okay, like group 1 elements are having low melting point, but they are having high melting and boiling point. So why they are having high melting and boiling point? First of all, um, you need to know that um, their melting and boiling points. Number one, I can say melting point and boiling points of transition elements are higher than what? Are higher than what? S and P block elements are higher than what? S and P block elements, right? S and P block elements. Like if you can see the periodic table, on the left hand side you have S block elements, I mean to say group 1 and group 2 metals, and on your right hand side you have group 3, group 4, group 5, group 6, group 7. They are P block elements. So the concept is that the melting point and the boiling point of transition metals are higher from the left hand side and then the right hand side. So they are at the top. They are having high melting point and boiling point. So Um, Of course, they are metals. Of course, they are metals. So obviously, whenever we are going to discuss the metallic, like melting point and boiling point, so we are supposed to introduce metallic bonding, isn't it? Metallic bonding. You know, if you remember in IGCSE when we used to discuss the melting point of group 1 elements and the group 7 elements and the group 7 elements. So, you know, you remember we used to say as we go down the group, as we go down the group, melting and boiling point decreases. I'm talking about group 1. Why? Because the metallic bonding, metallic strength decreases down the group. As we go down the group, size of cation increases. Size of cation increases. So its attraction with the C of delocalized electron decreases. So the force of attraction decreases. So less energy would be required to melt or boil. Okay, so that's why I can say down the group, melting and boiling point decreases. So what is the point here to discuss that whenever you are going to discuss the melting and boiling point of the metal, so you need to introduce the term metallic bonding. You need to use the term metallic bonding. But what if you are going to discuss the melting and boiling point of a halogens? So since they are non-metals, so you know for a non-metal, we are supposed to introduce the term IMF, intermolecular force. IMF, intermolecular force. Okay, so as we go down the group, I'm talking about halogens. So down the group, melting and boiling point increases. You know why? Because IMF increases as the number of electron increases. So same goes for the transition metals, as I'm telling you that they all are metals. Okay, as I'm telling you that they all are metals, so we are supposed to introduce the term metallic bonding. Okay, so melting point and boiling point is related to the metallic bonding. Okay, so I can say that in metallic bonding, in metallic bonding, in metallic bonding, I can say porous and 3D electrons. Porous and 3D electrons are involved. Are involved. Okay. So what would be the effect if they are involved in a metallic bonding? So I can say that more electrons, I can say that more electrons means strong metallic strength, like strong metallic bonding. When there would be strong metallic bonding, so I can say that more energy. I can say that more energy will be required. More energy would be required to melt. So that's why we can say the melting and boiling points of a transition elements are higher. Okay. You know why? Because also you can say that 4s and 3d electrons are delocalized. 4s and 3d electrons are delocalized. I'm supposed to write this one so that you can understand in a more better way. So I'm supposed to write that 4s and 3d electrons are delocalized. You know, delocalized means that they are moving. Delocalized means they are moving. When they are moving, so I can say that there would be a very strong electrostatic force of attraction between the cation and a sea of delocalized electrons. So that's why the melting and boiling points of the transition elements are higher. Okay. Okay. So that's all for the melting and boiling points. Uh, then we have to discuss.
the conductivity. Then we have to discuss the conductivity. The conductivity is just similar. The conductivity is just similar to, you can say, S block elements. Of course, P block elements are, uh, I can say, bad conductor of electricity since they all are non-metals. Like all, not all, but most of the P block elements are non-metals. Okay. So number two, I can write conductivity. Conductivity is almost same. Conductivity is almost same. But remember, there is an exceptional case that the conductivity of copper is higher. Conductivity of copper is higher. Conductivity of copper is higher generally. Okay. Then what about atomic radius? Of course, in a physical manner, we have discussed all, like if you remember in AS, we used to discuss group 2 elements, we used to discuss group 7 elements, and we used to discuss period 3 elements. Remember? We used to discuss period 3 elements. So in all inorganic chemistry, we discussed atomic radius, like it increases down the group, it decreases across the period, if you remember. So in the same way, we are supposed to discuss atomic radius of a transition elements. Okay. So as we know that when we go across the period, so atomic radius decreases. Remember, as we go across the period, atomic radius decreases. Let's talk about sodium and chlorine to get an idea. It would be more clear. Sodium is 11 and chlorine is 17. If you will be drawing an electronic configuration of sodium and chlorine, I can say that sodium would be having three shells. Sodium would be having three shells. Let's say this is the nucleus. It would be having the first shell having two electrons. Then it would be having second shell would be having eight electrons. And it would be having its third shell having one electron. Same goes for the chlorine, as you can draw electronic structure for chlorine. So in the first shell, you would see two electrons. In the second shell, you would see eight electrons. And in the third shell, you will see seven electrons. Since as we go across the period, I mean to say, when we go from left to right in the periodic table, so left to right, the total number of shell remains same. The total number of shell remains same. Okay. When the total number of shell remains same, so why the size decreases? So you can see in the nucleus of sodium, there would be 11 protons, and in the nucleus of chlorine, there would be 17 protons. So the force of attraction between the outer electron and the nucleus would be higher. That is known as nuclear attraction. Okay. And in the case of chlorine, of course, it has more protons, it has more electrons. So when you have more electrons and more protons, so the attraction would be higher. And when you have less electrons and less protons, so the attraction would be lower. Okay. It's all about attraction. It's all about attraction. So that's why, due to the stronger nuclear attraction between the protons and electrons of chlorine, so the size of chlorine is smaller. है ना? Okay. So across the period, size decreases generally. So what about the transition elements? So what about transition elements? Of course, I can say that for the transition elements, also the size decreases. Okay, size decreases. But there is a very important statement that I'm going to tell you. Number one thing is that atomic radius decreases. Atomic radius decreases, but there is a very important thing that you need to know is that uh, but 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 they but they do not decrease as much like like in other periods. Like generally across the period size decreases, but they are not following the same pattern. If other period elements would be decreasing sharply, this is very important statement, okay? If other elements would be decreasing sharply, so these elements are not going to follow the same trend. There is a difference between the transition elements and other elements, okay? But in fact, the decrease in size is very smaller, or I can say negligible. This is very important point. Remember, okay? I'm repeating. The decrease in size of a transition elements are almost equal, like negligible, I can say. You know why? You know why? Since the orbital is the same. You can see orbital is the same, like subshell is the same. 3D, 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 until you will be writing down an electronic configuration of zinc, isn't it? 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. Subshell is the same. When the subshell is the same, that's why I can say the decrease in size would be negligible. So what am I supposed to write in this one? I can say that I can say that uh, atomic radii, atomic radii are roughly equal. Atomic radii are what? Roughly equal. This is very important. Okay, are what? Are roughly equal. Okay, so then what about another one? Ionization energy. Then what about another one? Ionization energy. Ionization energy is related to the size. Hopefully you know this thing. Ionization is inversely proportional to atomic radius. Okay. Ionization energy is inversely proportional to atomic radius. When the atomic radius is smaller, when the atomic radius is smaller, so the ionization energy would be higher. Like I mean to say more energy would be required to remove an electron. Since there would be very strong electrostatic force of attraction between the nucleus and outer electron, isn't it? So that's why I'm saying, that um, as we go down the group, size increases. It would be easy to remove an electron, but what if when we go across the period, like I mean to say from left to right, since the size is going to decrease, so more energy would be required to remove an electron. Okay, as I told you about the atomic radius of transition elements, since they are just like similar, they are roughly equal. They are roughly equal. So it means that ionization energy would be following the same pattern. Also, one thing that is very important, if you remember when I was telling you an electronic configuration at that time in the last class, so I told you that let's say it's a normal scandium. This is an electronic configuration of scandium. Okay, so generally scandium has a +3 charge. So when I told you that it's going to be +3, so you need to remove 3 electrons. Listen carefully. You need to remove 3 electrons. So first of all, you have to remove electron from 4s, then 3d. It's a concept, remember. It's a concept. You must remove electron from 4s first, and then you have to remove electron from the 3d. Okay, first of all you need to remove electron from 4s, whether you have any element, whether you have any of the metal, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, those metals. Of course we are going to discuss the 3D series. Okay, in the syllabus we have 3D series, so we only discuss from scandium to zinc. Same pattern will be followed by the 4D series, of course. So always we will be removing electron from 4s, scandium, titanium, vanadium. Since we are removing electron from the 4s subshell, okay, so then I can say that almost like the ionization energy would be the same. Okay, ionization energy would be almost same. It doesn't mean that it would be 100% same, since we know that we are going across the period, right? So size is going to decrease. Whether the decrease in size is negligible, but it decreases. When it decreases, so ionization energy should increase. But the increase in ionization energy is negligible. But it is. You must know the concept behind it. Okay. So I'm supposed to write um, ionization energy ionization energy, okay, slightly increases. Ionization energy slightly increases across D block. So why? Why? Because in ionization energy, of course, I'm talking about the transition elements. So electron is removed from 4s. From 4s. Okay. So that's why I can say that it would be having the negligible effect on the ionization energy, right? And also across the period, nuclear charge increases, right? As we know that when we are moving from left to right, 3D, 1, 2, 3, 4, 5, 6, uh, we are going to add more electrons. What does it mean? We are going to add more electrons. So there would be having a stronger nuclear attraction, okay, stronger nuclear pull. So more energy would be required to overcome that pull, isn't it? So that's why ionization energy is going to increase. But again, I'm saying this increment is not as this as the same as the other like period elements. Okay. Hopefully you understood this point, what I mean to say. Uh, then uh, I can say they have a variable oxidation state. They have a variable oxidation state. Why they have a variable oxidation state? You know, what's the reason? They have empty orbitals. They have empty orbitals. Remember, they have empty orbitals. So I'm supposed to write as as they have empty orbitals. As they have empty orbitals. So that's why. Okay. So like sometime they will be promoting their electron from one orbital to the another orbital. So since they have a vacant space, it doesn't mean that all the elements would be having a vacant space. No, only they have a vacant space. They have empty orbitals. So of course there is a more space. Like let's say you are going to your school and you are the first one that like you came today, like you are the first one. Okay. Now like you went to your class and then you saw that all the chairs are, you can say, there is no one in the class. Okay. So it's up to you whether you can select any of the chair. Okay. All chairs are, like, you can say, it's up to you. So, and in other case, let's say when I would be late, so I will see that everyone is there, only one chair is left. So I have no option. I have to sit on that chair and that's it. But what if I can see all the chairs that are empty? So of course I have an option. I can do anything. I can do anything. Remember, so since they have empty orbitals, okay, so we have a vacant space. Sometime they would be having +2 charge. Sometime they would be having +3 charge. Sometime they would be having +5 charge. Sometime they would be having +7 charge as well. The maximum oxidation number for manganese is +7. That's the highest. That's the top line. Like if someone asks what's the maximum oxidation state they are going to have, so you can say that +7, and that goes to like I can say manganese. Okay, that goes to like manganese. So since I want to say that they have a variable oxidation state, if you remember, um, sometime iron is 2 plus, sometime iron is 3 plus, right? Sometime chromium is 3 plus, and sometime chromium is +6, isn't it? So etc, we have a lot of ions like that. Okay, so they have a variable oxidation state. And then after discussing the like orbitals, now we are going to discuss the complex formation. Now we are going to, this is the very important property of a transition elements, that they are going to form a complex compound. You know, I can't say that group 1 elements are going to form a complex compound. No, only the transition elements are going to form a complex compound. Uh, like um, like we have a very famous complex compound that is going to be copper sulfate, which is also written as like that. It's a very simple example, okay? Whenever you can see copper +2, that is blue, so this is going to be hydrated copper sulfate. If you remember, you have learned in the previous classes that we have two types of copper sulfate. We have anhydrous copper sulfate and we have hydrated copper sulfate. Okay, anhydrous copper sulfate is white, and hydrated copper sulfate is blue. Anhydrous copper sulfate is white, and hydrated copper sulfate is blue. Okay, so hydrated copper sulfate is blue means that water water is going to attract copper 2 plus ion from 6 sides. That's why I have written CuH2O, like taken 6. Okay, this is a kind of complex compound. This is the shape of complex compound. So you will see a major difference in writing the normal compound or a complex compound. So this is one of the example that I can see over there. So what are complex compounds? Let me tell you this one. Complex formation, I can say, okay? Uh, Complex formation. So basically, you need to understand the term complex. Complex is a combination of metal and a ligand. Complex is a combination of metal and a ligand. Okay, complex is a combination of metal and ligand. I can say in an easier term that when the metal, that is a transition metal, is going to react with a ligand, it's going to form MML. It's going to form ML. This is known as complex compound. This is going to have what? Complex compound. Okay. So when the metal is going to make a dative covalent bond with a ligand is known as a complex compound. So in other words, I can say that, in other words, I can say that metal is dative covalently bonded with ligand. Dative covalently bonded with ligand. Okay, it's mandatory. It's mandatory that it must have a dative covalent bond, right? It must have a dative covalent bond, not other than this. And hopefully, you know what's the dative covalent bond. When we used to discuss HCl or CH4 like that. So uh, it was mutual sharing of electron. You know what do you mean by mutual sharing of electron? Like 50-50% sharing. Let's say if electron is shared by the left hand sided non-metal, so the same electron would be shared by the right hand sided metal, like the non-metal. So one electron. Both elements are going to share their one electron. But whenever we discuss the dative covalent bond, so it's kind of something else as compared to the normal covalent bond. In this bond, only the single element is going to share two electrons. So it's a sharing of electron pair, not a single electron. That's a major difference between the normal covalent bond and a dative covalent bond. Okay. Uh, okay. Then I can say that metal, they are going to have empty. They have empty orbitals. Or I can say that ligand, what is ligand? Ligand means that they are electron donor. Ligand means they are electron donor. Okay. So ligand will be donating its electron to the metal and they will be making a dative covalent bond just like that. It's an empty orbital of M. This is a ligand having lone pair of electron. I'm going to share my screen. Wait. This is a ligand having lone pair of electron to this empty orbital. So so I can say that. So I can say that it's known as ML. So it's a dative covalent bond, right? This is an introduction of a dative covalent bond. Simple, simple. Or, or then we need to know some other things as well in this one. Uh, Let me tell you the representation like that. M L N plus minus N. This is called metal. This is called no like the ligand. This is number of with metal by a ligand, and this is an overall charge. Simple example. Let me tell you this one. Okay, this is plus 2. Copper is plus 2, and this is H2O. In this case, water is going to have a lone pair of electron. So it's known as, or I can say, it can be written as okay. This is an example of a simple complex compound. Water is acting as a ligand. Since it has a lone pair of electron, it's going to shift. It's going to donate its lone pair to the copper plus 2. So they are going to form a complex compound. Right, right, okay. And then we have, and then we have, what do you mean by ligand? What is ligand? Ligand means substance which is an electron pair donor. Do you remember the reaction mechanisms from AS? We used to discuss nucleophiles, isn't it? We used to discuss nucleophiles. What do you mean by nucleophile? Nucleus loving means that they are going to have a negative charge. But we used to say that water has no charge, but still it has, what can I say? Still it is acting as a ligand. What's the reason behind it? If there is no charge on water, so why water can act as a ligand? So you know why? Because on an oxygen, there is a lone pair of electrons. So as I told you, what's the condition to be a ligand? So there must be a lone pair of electron if they have some charge or not. Okay, like I can say ligands may have negative charge and they may have no charge. In both cases they will be acting as a ligand since they are having lone pair of electron. Let's say I'm asking ammonia has one lone pair of electron on the nitrogen atom, isn't it? So when in ammonia there is a nitrogen, there is a lone pair of electrons. Since it has a lone pair of electrons, so ammonia can act as a ligand. Okay, so it's not mandatory to have a negative charge, but it is mandatory that when something is going to have a positive charge, it would not be acting as a ligand. So what are the ligands? They are electron pair donors. There are two types of ligands. Number one, negative ligand. Like let's say, let's say OH minus, sulfate 2 minus, NO3 minus, etc. We have another ligand as well. They would be having a negative charge. Neutral ligand is H2. Ammonia and like water. That's it. TC. Since ammonia doesn't have a charge, but it acts as a ligand, it has a lone pair of electrons. Since water has no charge, it has a lone pair of electrons. It can act as a ligand. Water has two lone pair of electron, and ammonia has one lone pair of electron. Okay. Then we can classify ligands in a far way better. Like I can say there are three types of ligand: monodentate, bidentate, polydentate. What do you mean by this? Like ammonia has two lone pair of electrons, so it can donate its two lone pairs. It's a bidentate. Like generally I'm saying when something is going to donate three lone pairs of electron, like they are going to have three lone pairs, just like EDTA, EDTA, ethylene, diamine, tetraacetate. It's the formula I would be telling you. It's a hexadentate ligand. It has six lone pair of electrons. It can donate six lone pair of electrons. It's called polydentate ligands. The ligand which would be donating one lone pair of electron would be known as monodentate ligand, and the one which is going to donate two lone pair of electrons, they are known as bidentate ligands. Okay, bidentate ligands, and the one which are going to donate more than two electrons, so they are known as multidentate or a polydentate ligand. So they are known as multidentate or a polydentate ligand. Right? Easy. It's easy. So I can classify it. I can classify it. uh, Number one is mono monodentate. Monodentate ligand. Then I can define monodentate ligand as the ligand which can donate one lone pair of electron and makes one dative bond. Okay, and makes one dative bond. What are the examples? Examples are some of the example I remember. This one, this one, this one, this one, this one, etc. They can only donate. They can only donate one electron. That's why they are known as monodentate ligands. That's why they are known as monodentate ligand. In the same way, we have bidentate as well. In the same way, we have bidentate as well. So, what do you mean by bidentate ligand? Of course, the one which will be donating, the one which will be donating two electrons. Like, I mean to say, two lone pair of electrons. Okay. So then we have a bidentate ligand. Bidentate ligand. Same definition, same definition. But which can donate two lone pair of electrons rather than one and makes two dative bonds. And makes how many dative bonds? Two dative bonds, right? So this is all about the bidentate ligand. This is all about the bidentate ligand. Okay. So what are the examples? C2O4 2 minus oxalate ion. We have ethylene diamine. This is also a bidentate ligand. Okay, etc. Then we have polydentate ligand. Number one, which can donate, which can donate hmm, more than two electron pairs, which can donate more, oh my God, which can donate, which can donate more than two lone pair of electrons, which can donate, mhm, which can donate more than, which can donate more than two lone pair of electrons, and and makes more than two dative bonds, and makes more than two dative bonds, more than two dative bonds. That's called polydentate ligand. What's an example? What's an example? E D T A minus 4. It's a ligand which can donate six lone pair of electrons. It's a ligand which can donate six lone pair of electrons. That's it for the ligands. That's it for the complex compounds. Then we would be discussing some formation of the complexes, some how to find out the charges, how to find out the coordination number. So we will be discussing the same thing in the next class. Okay.